Hello and welcome. I'm Diane Okonski, your host for today's program. Before we get started, I just want to say thank you to our donors and INLUS members that make our webinars, classes, scholarships, and grants possible. If you are not yet a member of the INLUS, please consider joining us at inlus.org. Your questions today are welcome, and we encourage you to submit them using the Q&A feature and Zoom, and we will answer as many as possible at the end of the presentation. I am pleased to have with us today Kári Valgeirsson. Kári holds a bachelor's degree in geology from the University of Iceland and a master's degree in energy sciences, specializing in geothermal energy from Reykjavik University. Over the past 3 years, he has been working at the Geothermal exhibition, where he has developed expertise in geothermal systems and their behavior, high-temperature geothermal power production, and the utilization of low-temperature geothermal systems for direct heating. So, Kári, welcome. Nearly 3 years ago, I was able to tour the exhibition just outside of Reykjavik, and it was just so impressive. It was better than anything I had expected. And after the tour ended, I felt like we really needed to have a presentation. So I'm very happy you're able to join us
Yeah,
today, and I'll just turn it over to you.
thank you so much for that. And yeah, I'm also very happy to be doing this presentation for you over here. And today we are going to talk about geothermal in Iceland. And now I'm gonna share my slides over here. Should be coming up right now. Yes, very good. So, like Diane said, my name is Kári Valgeirsson, and we are going to talk about, I'm going to talk about geothermal in Iceland, and specifically maybe about this geothermal power plant that I've been working here for the past 3 years, the Hellisheiði Geothermal Power Plant, and geothermal utilization in Iceland. Now we will begin kind of with this company that we have over here for the power plant itself. The power plant is owned by the company Orka Náttúrunnar, or On Power in English. And On Power is a subsidiary company of Reykjavik Energy. Reykjavik Energy, like the umbrella company, owns 4 subsidiary companies. Veitur, which is the one here on the left-hand side, the distribution of electricity and hot water inside the capital area. Ljósleiðarinn, which is the fiber optic cable company. Orka Náttúrunnar, On Power, producer and seller of electricity. And then Carbfix, our own carbon sequestration company. Now we have this umbrella company over here, and we are mainly going to talk about Orka Náttúrunnar, or On Power. And On Power is the largest producer of geothermal energy in Iceland, both in terms of heating and electricity, but we are the second largest electricity producer. That is because the national power company has a lot more hydropower capacity than us over here. But we can say that we are the largest geothermal energy provider in Iceland. On Power has three power plants, 2 geothermal and 1 hydropower plant. We have the hydropower plant called Andakíl, which is producing about 8 megawatts of electricity. It's more of a historical power plant. Then we have Nesjavellir, which is on the other side of this mountain that we're in right now. Which is producing about 120 megawatts of electricity. And then this power plant over here, Hellisheiði Geothermal Power Plant, producing about 303 megawatts of electricity. And these 2 geothermal power plants, Hellisheiði and Nesjavellir, produce about 550 megawatts of thermal energy or hot water that goes to the capital area. Now we're going to talk about a lot of geothermal things. So we have this image over here that is kind of explaining why we can have all of this geothermal power potential in Iceland. Now, these kind of orange lines on this map over here, this is a map of Iceland, of course, and this orange line is representing the age of the bedrock in Iceland. However, the age of the bedrock is kind of directly linked to the mid-Atlantic ridge. The mid-Atlantic ridge is a divergent plate boundary between the two tectonic plates that we have here in Iceland. We have the North American tectonic plate over here in the west, and then we have the Eurasian tectonic plate over here in the east. And this is, like I said, a divergent plate boundary, which means that these two tectonic plates, they are separating from each other. The separation is approximately 2 centimeters per year on average for the entire island. But we have two major geological phenomena happening on the island itself. We have the divergent plate boundary, the mid-Atlantic ridge, and then we also have a mantle plume, or a hotspot. That is this yellow circle here. Now, the mantle plume, or the hotspot itself is the surface manifestation of this mantle plume. So this mantle plume is where you have a column of really hot magma material comes from really deep down from the earth, and therefore drives the hot magma material to the surface of the earth, and therefore forms, for example, the island Iceland. But now other notable figures in hotspots or mantle plumes are, for example, the Hawaiian Islands. And if we take the Hawaiian Islands, for example, it is theorized for hotspots and mantle plumes that they stay kind of in the same place, and then the tectonic plates are moving above them. So this is why, for example, in Hawaii, it forms like this chain of islands. But here in Iceland, we have both the separation of the tectonic plates and the hotspot happening at the same time. So this is kind of why we have the big whole island Iceland instead of an island chain. Now, you would also figure that with the orange line represented on the slide over here, with the youngest bedrock, we have a lot of volcanoes, because they therefore put out the youngest lava rocks in Iceland. And the volcanoes in Iceland are mostly following this orange line over here. And today, the most recent volcanic eruption that we had was here on the Reykjanes Peninsula, occurred like several months ago. And we will probably see some seismic and volcanic activity in that area for how many years, that is still unknown. But this is like, there's a really good Icelandic word for this, eldar, or fires. We are in like this kind of stage right now. But the further that you get from this orange line, the older the bedrock itself is. And the oldest bedrocks in Iceland are here on the west fjords, and then also here kind of in the east fjords. And this is why, because of the separation of these tectonic plates. Now, these active volcanoes, some of them hold what we call a high temperature geothermal system. Now, for a high temperature geothermal system to form, we essentially need to have three things to be present. First, we need to have the permeable bedrock formations, like the basaltic rock that we have everywhere in Iceland. It's about 80–85% basaltic rock in Iceland. Then we need to have a lot of water, and it's always raining here in Iceland, so we have a lot of water. And then we need to have the heat source itself. The heat source is, of course, the active volcanic system that we have. And so the water will seep through these permeable bedrock formations, gets heated up by this heat source, forms this high temperature geothermal system, and then we can utilize that with our geothermal power plants. And these red dots that you can see on this map are where we have these high temperature geothermal systems. But then we also have these black dots all across the entire island. These black dots are what you call low temperature geothermal systems. Now, as you can see, the low temperature geothermal systems are really scattered throughout the whole country and are located in like the older parts of the island. And this is the reason why I started with the formation of the island, is because the further away from this orange line over here that you get lower temperature in the bedrock, but you could theoretically still utilize this low temperature geothermal system. The categorization between these two, the low temperature and the high temperature, for the low temperature we categorize them at 1 kilometer depth, and the temperature ranges from 30 degrees Celsius to about 150 degrees Celsius. So it's still above the boiling point of water, but still not enough heat and pressure to produce, for example, steam. But then the high temperature ones, those are categorized also at 1 kilometer depth. Then you have 200 degrees Celsius and above. That is like the technical definition between these two geothermal systems. And therefore, the low temperature areas over here are mainly used for hot water production only. But the high temperature geothermal systems are used for both hot water production and electricity. And this is why, where this green circle over here is where we are located in. The Hengit volcanic system is the system that the Hellisheiði Geothermal Power Plant is utilizing. And that's a high temperature geothermal system, and this is where we can use both hot water and steam to generate electricity. Now, in Iceland, we have about roughly 7 geothermal power plants in Iceland. It depends on kind of how you define a geothermal power plant. I like to define them as above 10 megawatts of electricity, and we can call Bjarnarflag the oldest geothermal power plant, even though it's only producing about 3 megawatts of electricity. It is still the oldest geothermal power plant in Iceland, so I always like to include that, but some people don't, so this is my categorization. But yes, we have 7 geothermal power plants. There are 4 here in the southwest, and there are 3 up here in the north. And these 7 geothermal power plants are all producing electricity, and the electricity mix in Iceland is about 30% from geothermal. But like I talked about in the beginning, most of the power or the power producer in Iceland is from hydroelectric power plants. So the other 70% comes from these hydroelectric power plants, which are from the national power company. But then the electricity mix in Iceland is 30% geothermal, 70% hydro. We can roughly say that Iceland does produce 100% renewable energy, and the utilization is kind of like that. There are places that do have diesel backup generators, but that is if the weather conditions are so bad and if the national grid itself goes offline. But like I said, we produce 2 things over here. We produce not only electricity, we produce hot water. So the utilization of hot water or geothermal hot water in Iceland in terms of heating is about 90%. 90% of houses here in Iceland are heated up with some kind of geothermal energy. That is both from geothermal power plants that we have over here, but also because of these low temperature areas that are scattered throughout the whole country, where you can theoretically drill directly into the earth and extract the hot water directly from the ground. Case in point, we are located over here, and I don't know if you can see it, but there are a lot of black dots around the capital area, Reykjavik, over here. So we have constant production of hot water and electricity kind of, but heating demand goes up and down over 1 year period. So over the winter time, heating demand is the highest. But our constant production is, for example, just over here. So how do we use or produce more hot water for the rest of the demand, we utilize low temperature sources inside the capital area. So we have just direct low temperature boreholes inside the capital to meet the heating demand over the winter time. But then over the summertime, heating demand goes down. And so we try to rest these low temperature boreholes inside the capital so they can replenish, and then therefore we can also maximize utilization with them over the winter time. This is a really good sustainability approach to do this, because you can drain a geothermal system, but by doing it like this, when you're lowering the production when demand goes down, then you're not depleting the system. So, introduction to geothermal and like the geological senses here in Iceland. Like I said, this power plant is the Hellisheiði Geothermal Power Plant, and is by far the largest geothermal power plant here in Iceland, and even one of the largest geothermal power plants in the entire world. And at this facility we are producing these 303 megawatts of electricity and around 200 megawatts of thermal energy, and this is done by this high temperature geothermal system like I was talking about before. But how? How do we do this? How can we have this geothermal power here in Iceland? And how do we utilize it? The first thing that you need to do for the power production is that you need to drill a production well. The production well at this facility goes to an average depth of about 2 kilometers. And at this 2 kilometer depth, we have temperatures at about 300 degrees Celsius. So it's fairly hot down there. And what we are extracting from each individual borehole is what we call the geothermal fluid. The geothermal fluid is kind of this water with a lot of dissolved minerals inside of it. So water, for example, comes down as some kind of precipitation, be it rainwater, snow, glacier melt or something like that, that seeps into the bedrock like I was talking about before. But because it heats up in the bedrock, it will dissolve some of the minerals inside of the rock formation itself. And therefore we call this the geothermal fluid, because this is just water with a lot of dissolved minerals inside of it. But because we also have a lot of heat down there, you get kind of a mix of geothermal fluid and steam together in one borehole. Some boreholes or production wells can be drier, have more steam in them. Some of them can be more liquid sense. But because we get most of the time both steam and geothermal fluid together in one pipeline, we need to separate them from each other. We separate them in what we call the steam separators. Here at this facility they are horizontal. They can be vertical, but here at this facility they are horizontal. And they are gravity based, and so the steam wants to go up and then liquid wants to go down. So we separate them kind of with gravity. Then after the separation states, the steam goes through the inlet pipeline for our high pressure turbine units. Now this geothermal power plant works kind of the same as any kind of steam power plant would operate, in that way that the steam hits the turbine blades. All of the turbine blades are connected to an axle. This axle is connected to a generator, and the generator generates the electricity itself. This is kind of the same principle as a nuclear power plant would operate. You boil water to get steam to drive turbines to produce electricity. But here we are using kind of the heat or the steam from the earth itself, and therefore we get this 7 bar pressure in the high pressure turbines over here. Now you would also think that, if somebody is really into nuclear power plants, you would say that 7 bars is kind of low pressure, and that is kind of correct in that way that all things geothermal is lower pressure than kind of any other type of power generation, but here we call this high pressure because it just comes up naturally, and this is what we can utilize. Now, like with any other kind of the design choice is yours, but if you have power production, most of the time you would have a condensing unit. This is where you condense the steam back into water, but to cool down the condensing unit, you need to have some kind of cooling mechanism, and this is where we have cooling towers. And cooling towers is the big thing that you can see at the back of power plants where there is steam coming out of it. However, there is another thing going on at this facility. Because there is so much energy still in this geothermal fluid, we lower the pressure even more to get low pressure steam for the low pressure turbine unit. And this is why we can say that we have 6 high pressure turbines and then 1 low pressure turbine with a combined power output of these 303 megawatts of electricity. Yeah, and then the geothermal fluid, we have used most of the pressure from it, but it's still very hot. Here on this slide it's called separated water. Separated water is the same thing as the geothermal fluid, so so nobody is confused in that regard. But this geothermal fluid is then introduced to the thermal plant, where we are producing the hot water, but the thermal plant over here uses what we call a heat exchange. And I will talk about that more in a bit. But the rest of the geothermal fluid after that has exited the thermal plant or the heat exchangers. It is simply re-injected into the ground to kind of keep this renewable energy cycle going. Because here on the left you are extracting, and then it goes through the production site over here, and then on the right it's re-injection, so it can kind of be used again and again and again. And this is why we can kind of keep this power cycle going, because like I said before, with the low temperature boreholes, it's true also for these high temperature boreholes, you can drain a geothermal system, but by re-injecting the geothermal fluid back into the ground, it kind of keep this renewable energy cycle going. And that's not only for the geothermal system, but that's also so we can continue producing power in Iceland and get some money from that, we can say also. Yeah. But the hot water production. The hot water production uses a heat exchange. Okay. So we get cold, fresh groundwater in the beginning. Here at this facility, we kind of use this cold water as another kind of cooling mechanism. So we use this cold water that we get just from outside the area over here, and we use that also for the condensing units. After it has cooled down the steam that goes through the condensing unit, the cold water is now preheated or kind of hot right now, and therefore that is introduced to the thermal plant, and from the thermal plant we heat it up to about 84 degrees Celsius, and then we send that into a distribution center in the capital area, where we distribute this hot water into kind of each individual home, and then we can utilize it by either turning on our radiators, tap water system, showers and stuff like that. And what is good also from this facility over here is that we produce this geothermal fluid, this hot water, and we produce it at this 84 degrees Celsius, but then it arrives in the capital about 82 degrees Celsius. So we only lose about 2 degrees Celsius for this 25 kilometer way. And this is because we have it very well insulated. We have it insulated with what we call rock wool. And the rock wool is produced here locally in Iceland, in Sauðárkrókur. And the rock wool is essentially just this regular basaltic rock that we find here in Iceland, that we spin, or first we melt we melt it down and then spin really fast in kind of like a candy floss machine. We create these fibers, compress these fibers together, get the rock wool, and that is what we use to insulate these pipelines. And then, like I said, yeah, it goes into the capital area and we distribute it into each individual home, and then we use it like that. So this slide over here is kind of the whole production side of this Hellisheiði geothermal power plant. We get the geothermal fluid and steam together into the steam separator, separate the steam for the turbine units. The geothermal fluid is then introduced to the thermal plant to use to heat up cold fresh groundwater, but the rest of the geothermal fluid is re-injected back into the system over here. Very good. Now, what we kind of want to do next. Now we're going to go into the innovations here at the power plant. Well, so we want to go even deeper. Like I said before, we have the production wells at this roughly 2 kilometer depth, and then we have also the re-injection wells at roughly 2 kilometer depth also. They are kind of this facility over here is kind of the only facility in Iceland, geothermal power plant, that is re-injecting at these really deeper parts. So, but we want to go even deeper. So this is a collaboration with all of the power companies in Iceland and a lot of the engineering offices here, is to go deeper and to get hotter fluid. So there is kind of two things with this. This is called the IDDP, or Iceland Deep Drilling Project. And so this is number 3. First it was drilled in 2009 in Krafla in the north. There they wanted to go to this 4 kilometer depth, but they only went to about 2 kilometer depth before they hit a magma intrusion. Yeah, and that was not very good, but I mean, for a brief moment they had the smallest eruption ever happening in Iceland, but they could close it up, so there was nothing to worry about in that regard. That was number 1. Number 2 was done in Reykjanes, where that was IDDP number 2. That was drilled in 2016 to 2017. And there they drilled down to 4,600 meter depth. But unfortunately, that one caved in, kind of, so they could not produce anything from it right now. What we want to do here is that we want to drill to this 5 or 4 or 5 kilometer depth to check out if we can produce any power from that. And we are really looking forward to that. This will begin later this year. And there are kind of 2 things with deep drilling. You want to get deeper, of course, because then you get higher temperature. But you could theoretically, like happened in the Krafla in the north, is that you can theoretically, if you know of a magma intrusion or something like that, you could just drill into the 2 kilometer depth also, but you get hotter fluid. So we kind of want to have this as like the super hot project, we can say, rather than just deep drilling. Other places all around the world have done deeper drilling than here in Iceland, but they have maybe found 180 degrees Celsius there. If we go deep over here, as you can see in this middle slide over here, we are going into roughly 300 to 400 degrees Celsius. Now, there are 3 scenarios for this deep drilling or super hot project that we have. First, here on the left hand side, we would want to check out deep re-injection. Deep re-injection means that we will have a borehole that goes to maybe 4 5 kilometer depth, that we only re-inject the geothermal fluid back into the system to maybe get it into kind of the same boreholes that we have right now, and therefore we could theoretically, this is all just theory right now, we could theoretically have more power production in the already drilled wells that we have. So there is only one well that we would need to drill into to get more energy for the regular or conventional wells that we have over here on the left hand side. This is all theorized, of course, so theoretically we could do this, but the next step would be the main thing for this project, the deep production well. The deep production well would want to go to this 4-5 kilometer depth and get temperatures from 400 degrees Celsius and above. But what is tricky about that is that when you get into these, we can call these supercritical conditions, there are a lot more aggressive elements that are in this geothermal fluid. There's a lot of things in the steam, like more chlorine and stuff like that in the steam itself. And this is kind of not something that we know how to utilize on the surface. All of the machinery that we have over here is built to withstand more corrosive gases and stuff like that, but not in the same concentration as you would in the deeper parts over here at these supercritical conditions. So first we would need to drill at this depth, get the fluid to the surface, sample that and see what kind of metals we would need to be working with to see if there is any power production potential for this to happen. But then on the right hand side is the EGS. EGS stands for Engineered or Enhanced Geothermal Systems. So engineered or enhanced geothermal systems is that where you are kind of creating permeability in areas that have maybe less permeability. This is kind of what is going to be really big in, for example, the United States, is because the United States, especially the western coast of the United States, has a lot of heat potential, but does not have the permeability for water to flow through it. All right. So what you want to do is that you want to kind of create permeability, and this is what a lot of people have been asking us about over here. When you're creating permeability, isn't that fracking? Fracking is kind of the same principle. You want to fracture the earth to create more permeability, but this kind of EGS would not be at the same, what can we say, same pressures as you would in oil and gas fields and stuff like that. In oil and gas fields, that's much higher pressure than you would want to have in these kind of conditions. But then also for the scenario here on the right hand side is to have deep reinjection and also deep production. This is all just theorized over here, but the theory is for the middle one over here, the deep production well at the supercritical critical conditions, is that we would have 10 times more electrical energy per borehole. So the production, there is like an average electrical capacity for these conventional wells. It's about 5 megawatts of electricity at this area. It is theorized if we go into these supercritical conditions for the deep production, it will be about 50 megawatts per borehole. And that is kind of what we want kind of for the future, because geothermal, there are some downsides to it. I will not go into all of them today, but one downside is that if you are going to have a big power production, like for example the Hellisheiði power plant, you need a lot of boreholes. And so if you can have 10 times more energy per borehole, then there is less environmental damage on the surface itself. But what you need to kind of do then with the deep reinjection is to check out the metallurgy if you can have power production for that. All right. Now, there are two innovations that I want to talk about. That is this one that we are going to go into like later this year. But another thing that we have currently going on. Geothermal power plants do have some emissions. These emissions include, but are not limited to, carbon dioxide and hydrogen sulfide. Here at the Hellisheiði Geothermal Power Plant, we have established Steingerður or Silverstone. This project was to get the power plant to about near zero emissions. So we take, for example, the gases that come with the steam, the carbon dioxide and hydrogen sulfide, but because these are non-condensable gases, they will not turn into its liquid state at the back of the turbine with the condensing units, and therefore they are separated away from the steam. And what we do over here is that we put them into this scrubbing tower, which was the image before, and therefore we dissolve them in water. We create kind of like a regular bubbly water, and this bubbly water is also re-injected into the ground. And the bedrock in Iceland is mainly composed of basaltic rock, like I said before, and basalt contains a lot of calcium, magnesium and iron. When you re-inject these two gases in the water, it will free up some of the ions in the bedrock. It will kind of eat away the rock formation itself, and will free up some of the ions, for example the calcium, magnesium and iron ions, and therefore they will bind with the calcium, carbon dioxide, to form calcium carbonate minerals, for example, or magnesium carbonates and or iron carbonate minerals. Hydrogen sulfide will then react with the iron in the bedrock to form iron pyrite minerals on the ground, or which we can also call it fool's gold. Yes. So these are kind of like the big innovation styles that you can have at a power plant. Power plants do not only need to produce electricity and hot water or something like that and be this big gray boxes. You can also have innovations in them, and you can have them be in a pretty cool style like we have over here. But this was my last slide over here. Thank you so much everyone for listening to my presentation about geothermal. We can't hear you there.
Thank you so much, Kári. There we go. Yes, could you unshare your screen?
Yes, I can.
All right, and we do have questions.
Okay.
We do have questions. This has been just fascinating.
Yeah, of course.
And so thank you for joining us. The first question is, how deep is the reinjection and how much volume at a time? And does it trigger any seismicity or not noticeably compared to what's normal for an active volcano system?
That's a really good question, because I think I answered at least how deep the reinjection is, but I can tell you again, the production is about 2 kilometers, but then the reinjection is at about 2 kilometer depth also. Oh. And like I said, this power plant is probably the only power plant in Iceland that is doing these deep reinjections. Most of the other ones are doing at about 500 meter depth or something like that. Yeah, some of them, like for example the Reykjanes Peninsula, are recharged with seawater, so they don't need to do these deep reinjections over here. How deep is does it trigger seismicity? It can. It happened one time that it did trigger seismicity, like induced seismicity, but that was also because we were re-injecting into higher temperatures that we were expecting, and so we abandoned that well, and we are currently only using that as a monitoring well, but not as a re-injection well. we currently are not experiencing any kind of disruption with any of the reinjection at this facility right now. Yeah, but yes, we are in an active volcano, so we get a lot of seismic activity also. Yeah.
Okay, so is the volume of the reinjection equivalent to the volume of the fluid being drawn out?
We can think of the production side as roughly 100%, yeah, of course, because we are extracting 100%, but then the reinjection is at about 80% capacity. Some of it is just is escaped through what we call the emergency release valve, if we are doing maintenance or something like that, or through the silencers and stuff like that. So 80% capacity is still relatively good for a geothermal power plant.
All right. And can nearby seismicity or eruptions affect the output of the production wells? And if so, how do you accommodate those changes, and how do you monitor them?
Yeah. The eruptions that have happened on the Reykjanes Peninsula that are like 50 kilometers away from here as the crow flies have not had any effect on the production of this power plant over here. But if like big earthquakes can happen in this area, and a big earthquake happened in 2008, and there were 2 boreholes that lost a lot of power production from them because the area kind of shifted, like the downhole area shifted away, and so some of that water or liquid went just into other boreholes. So some boreholes got lower production, some of them got a little bit more. So it has some effect on where we have the boreholes located at, and we know of this risk because we are at this active volcano. So if something big like that happens, we would just need to check out first, directly afterwards, do all of them produce any more? Second thing is that can we divert some of the steam into into the other boreholes, and also can we open up some of the boreholes that we have kind of like halfway closed? Can we like utilize more from other boreholes? But yes, yeah, it can happen.
All right.
Yeah.
Well, the person asking these questions has just shared that he is an earthquake physicist, and he has one more.
Okay.
So he is in California, and one of
Okay.
the big concerns there is that anything messing with rock permeability
Mm-hmm.
might affect nearby faults or highlight the existing of previously unknown faults.
Mm.
Do you know if there's a parallel effort to identify more faults and or evaluate hazard on known ones in the area where you are planning to enhance rock permeability?
Uh, yeah. That's also the thing. Like we have not established where we are going to do the EGS, because we have kind of not. We first want to do the deep reinjection and the deep production just to see if that can work. But then the other thing is that we want to what can we say? We want to have this in a specific area where there is less permeability. Here at this site, the permeability ranges from 1 millidarcy to about 10,000 millidarcies, if I remember correctly. So it would not be in this area. Where that would be, I don't know. We have not figured that out. But yes, we can say that there have been permeability changes with reinjection, just with even just the shallow reinjection at the other geothermal power plants. But that has not had the effect of less production from those geothermal systems, at least not right now. Maybe more power production will have that effect, I don't know, but right now it is currently not doing that. Yeah. But like effort to identify more faults, yes, we kind of want to know as much as about one geothermal system as we can, not only because it fascinates geophysicists and earthquake physicists or something like that, but also because you want to know where your next well would be located at. If the well is in an area with bad permeability, but you don't know it, then you might not have any kind of power production from that well. You would want to know the right permeabilities, and you would want to know if you're re-injecting into faults that are letting the geothermal fluid escape from the system. Yeah. It's a big question and a long answer. Yes.
Well, Julian is very appreciative of it.
Of course.
The next question has to do with rock wool
Yes.
and the idea of rock wool. When and how was the product discovered, and what else is it used for besides insulating the pipes, transporting the hot water to the capital area?
Yeah. That's that. There are two things in that regard. One thing is that I know a lot of Danish people say that this is a Danish invention. I always like to say that it is an Icelandic invention. But the reason why I say this is because I had propaganda from one of my old colleagues over here, and he said that yes, this is an Icelandic invention. But the reason, that's also the thing. What can we say? When was it first discovered? I don't know exactly about that, but I do know that we knew of rock properties, and that rocks are bad, have bad thermal conductivity, or bad in that sense, or worse thermal conductivity than, for example, metal. So we knew of that beforehand, but I don't know exactly the history of the rock wool itself. But I know that we have the production is here in Sauðárkrókur in the north of Iceland, and we use it also to insulate our houses in Iceland. That's the reason kind of why we have it on the pipelines themselves. If I remember correctly, they were using it first to insulate the houses, but then they said we have a lot of heat loss from the pipelines, even though they were insulated with foam, plastic or something like that. But then they said, oh yeah, let's just insulate it with this rock wool and see what happens. And it's a really good insulator for them, at least for the production of this power plant. Yeah.
Wonderful.
Yeah.
So we have another question. Looking ahead 50 years, how do you think geothermal energy in Iceland will differ from today?
50 years in the future, 2076. Very good. So in my opinion, I think that we will have more power plants in Iceland, of course, but maybe not a lot more. A lot of power plants a lot of the geothermal areas in Iceland are protected. So all new power generation needs to go through what we call the master plan, and the master plan is where companies can say hey, we want to have power production over here, and then they need to submit some proposals and stuff like that, and then the government can say can have the final say in saying yes, no, maybe, or on hold or protected or something like that. And so a lot of these high temperature geothermal systems, like for example geyser, that is has a really good geothermal potential, but I think we will never have power production over there just because of its natural beauty. But the landscape in Iceland is that we will probably be, like with the deep drilling over here, we will probably have a lot more power production in Iceland in areas that currently have power production. Meaning that this area over here, the Hellisheiði area, has kind of three distinct zones where you can have power production. It has the Hellisheiði just directly at the back over here. We have Skarðsmýrarfjall just on the left hand side, And then we have Hverahlíð, which is about 5 kilometers away from this power plant over here. But this is still all within the same kind of high temperature geothermal system. And therefore, this is why this answer is so kind of broad. I would always say that we would have just more power production in areas that currently have power production. So I think, yes, we have 7 geothermal power plants in Iceland today since 1969, and I think we will have maybe just 10 or 20 more or something like that. Today, the national power company is importing wind turbines to the island, and this is kind of the first time wind will be fully utilized in Iceland. So that is maybe what is also the next step. Have like both wind, hydro, and geothermal. Maybe some solar, maybe.
Okay. So that was my next question was going to be with the current setup of 70% hydrothermal and 30% geothermal. Do you see that as remaining relatively stable, or do you think that is going to change? That's more short term than 50 years out.
Yeah, but if we still, let's relate that to the 50-year question, because what is currently happening today in Iceland is that we have a lot of glaciers, yes, but what is currently happening all around the world is the climate, it's changing and stuff like that. It is getting hotter in Iceland, and a lot of the glaciers are melting away. So in Iceland we will have probably the highest power production in hydropower for the next 50 years until they disappear completely. And then after that, after these 50 years, we will, I don't know how the power production will then be after all of the glaciers will have gone away from Iceland, because we rely on a lot of them for our power production. But yes, in the nearby future, just like maybe in the next 10 years, we will see this number changing to maybe 65% let's say 60% hydropower, 35% geothermal, and then 5% from wind. I think this is my prediction. But the prediction for the Energy Authority in Iceland, that was in the slides that I got were from 2023, and if I remember correctly, their projections were that we would have like a carbon neutrality in all transportation in Iceland in 2040, and therefore we would need to double our power production in Iceland by 2040. Right now, I don't see that happening, unfortunately, because it takes a long time to develop new power production. But let's see if power production can be like smoother in the next couple of years. Yeah.
Okay. All right. Well, thank you.
Yeah.
And the geothermal exhibit is a real place. It's
Of course, yes.
Right on the Highway 1, the ring road, just outside of Reykjavik.
Exactly.
And what are the hours of operations, and do we need to make reservations to come in?
Yeah, so over the summertime, when it's summertime in Iceland, or for the exhibition, let's call it that, summer openings in the exhibition are from 9 to 5 every day until 31st of October, which is kind of not summer in Iceland, but it's still the summertime for the exhibition. And then from 1st of November to 31st of March, we are open from 9 to 4, so it's just a 1 hour difference. You can always come over here into the exhibition and just buy tickets here in the front. That is not a problem at all. But if you would want to have a guided tour where, for example, you will have a guided tour by me, you will need to go through our email address, which is sýning@or.is. Okay. And therefore you can just book tickets over there, but you can also just drop in over here and say, hey, I would like to do the self-guided tour, and therefore you can look at all of this displays while I'm not rambling about like I was doing this over here. Yes.
Okay, all right, and we will put that link in at in with our videos as we post them to our website and on YouTube.
Very
So,
good.
Kari, thank you so much. This has just been fascinating,
That's good.
and
Great.
it's really, really been interesting to learn how all of this works.
Of course.
Um, and before we go, I do have a couple of announcements. One is that on September 23rd at 8 p.m. Eastern, we will have a webinar by Dr. Elizabeth Ida Ward to talk about how the Icelandic sagas are informing archaeologists in North America as they are doing their research. So this is going to be a really interesting program as well, and I hope you mark it on your calendars. And then, literally within the last 2 hours, we have booked another webinar on Iceland, traveling around Iceland in the winter. So, our friends at Hey Iceland, who are also an INLUS business member, are going to talk with us about winter travel in Iceland, and we will also be paying a visit to one of their locations. So that's always interesting. We've had them do that a few times before. And so that will be October 26th at 5 p.m. Eastern. So that we will, keep up with the Icelandic hours and not have them join us in the middle of the night. And as always, the INLUS is very interested and willing to post your Nordic events on our calendars. So please drop us a line at info@inlus.org. And our events calendar will give you all the information that you need or that we have. So thank you again, Kari, for just a wonderful presentation. And thank you for all the attendees and for your great questions. So have a wonderful day. Thank
You
you so
too.
much
Yeah.
and
Thank you
bye.
also for having me. Thank you. Bye bye.